So today we're going to be putting everything we've been learning in calculus together to do something that was called curve sketching. And curve sketching is applying all of these different analysis methods that we've learned about using the first derivative and the second derivative and using algebra concepts that you already knew to draw a really accurate picture of a function without a calculator or a computer or anything like that. So I think that this is a really cool section of your textbook because you actually can draw a very accurate picture of something without using your graphing calculator or computer, and you can just do it all by hand. And I think it's really cool how much detail you can find out about a function just using your brain and your pencil and paper. So we're going to use everything that we know how to find so far, like an x and y intercept, analyzing domain and range of functions, determining where a function is continuous, if it has any vertical and horizontal asymptotes, where the function is increasing and decreasing, any relative extreme it might have, and then the concavity and inflection points that we just talked about using the second derivative. We're going to put all that information together onto a graph to make a really good picture of a function. So let's put all of that together and do an example. So we're going to analyze and sketch the graph of f of x equaling 2 over x squared minus 9, 2 times x squared minus 9 rather, all over x squared minus 4. So what we want to do first is analyze if this function has any asymptotes and see where the intercepts are. So maybe first let's figure out where the y-intercepts are. Now to find y-intercepts, you plug in 0 for x and see what happens. So in other words, we want to know what f of 0 is. So if we plug f of 0 in, we get 2 times negative 9 all over negative 4. So our negative signs will cancel out, and then we can cancel this 2 with this 4, and we're going to get 9 halves. So we have a y-intercept we know at 0, 9 halves. So we can go ahead and put that point onto our graph. 9 halves is about 4 1/2. So let's see, 1, 2, 3, 4. So we have a point right about there. And then we also want to see if we have any x-intercepts. So x-intercepts are where you set the function equal to 0 and solve. So if we set our function equal to 0, we have 2x squared minus 9 over x squared minus 4. If we multiply the x squared minus 4 over, we just get that 0 is equal to 2 times the x squared minus 9, which we can go ahead and factor as x minus 3 times x plus 3. Squish that in there. So that means that if we plug in x equaling 3 and x equaling negative 3, we'd get a 0 back. So we know that we're going to have x-intercepts at negative 3 comma 0 and 3 comma 0. So now we have two more points that we can put onto our graph. So we'll put those on. And the next thing we want to do is apply what we learned previously about continuity and horizontal and vertical asymptotes, because we can do all of this before we take any sort of derivatives and start working with those. So let's figure out our vertical asymptotes first. So abbreviate that as VA. So vertical asymptotes happen when your denominator is equal to 0 and there's nothing to cancel out with the top. So maybe let's go up here and rewrite this real quickly as our factored form. So x minus 3, x plus 3, because it makes it really easy to see where we have any holes or any vertical and horizontal asymptotes. And that's going to be x minus 2 and x plus 2 in the denominator. So our bottom is going to be equal to 0 when x equals 2 and x equals negative 2. And we can't cancel with anything in the top, so those are going to be our vertical asymptotes at x equals positive 2 and x equals negative 2. So we can draw those on as well. So see, before we even do any calculus, anything that's really hard, it might take some time, we can get a lot of details about a graph. And then before we start doing any calculus, we'll also do our horizontal asymptotes, which if you don't remember, this is when we do the limit as x goes to infinity of 2x squared minus 9 over x squared minus 4. Now, we know that the highest power on the top matches the highest power on the bottom, which means that we just have to do the ratio of the coefficients. So we have 2 over 1, or just 2. So we know that we have a horizontal asymptote at y equaling 2. So we'll also put that on the graph, and then we can start taking our derivatives. and analyzing our functions. So we've split our function up already into these three different intervals. And since we already have points in these intervals, we know that the graph is going to be up here in this middle section, and then over here in these two lower outside squares that we have drawn. Okay, so let's actually do some calculus. So let's find the first derivative of this function and analyze it so we can find any relative extrema and then find where our function is increasing and decreasing. So we can do our quotient rule. So we have 2 times x squared minus 9. So we're going to take the derivative of that first. So the derivative of that is just going to be 2 times 2x. And then times the bottom, so x squared minus 4. Minus the derivative of the bottom, so 2x times the top, so 2 times x squared minus 9. All over x squared minus 4 all squared. Just bringing in that quotient rule. Now if we simplify it to make it a little nicer, we're going to get, let's see, 4x times x squared minus 4 minus 4x times x squared minus 9 all over x squared minus 4 all squared, which if we factor that we get 4x, and then on the inside we'd have x squared minus 4 minus x squared minus 9. So let's see what that gives us. So let's see, all still over that x squared minus 4 squared. So that's going to leave us with 4x times our x squareds will cancel, and then this negative 9 becomes a positive 9, so we actually get times a 5 in there. So why don't we actually just simplify right away and make this a 20x over x squared minus 4 all squared. So that's our first derivative. So now we want to analyze that. So we want to find our critical values. So our critical values are where it's undefined. So this is going to be undefined at x equaling plus and minus 2, because those were our vertical asymptotes were before, and so those are going to stay here because that x squared minus 4 is in the denominator again. And f prime of x is going to equal 0. That's pretty easy to see because we just have a 20x there in the top. It's going to happen when x is equal to 0. So we have 3 critical values. So we'll do a sign chart over here for our first derivative. So we'll plug in -2, 0, and 2 on the bottom there for our critical values. We're going to put x's above the plus and minus 2's because that's where it's undefined, and a 0 above the 0 because that's where the derivative is equal to 0. So now let's just find some test values. So it looks like -3, -1, 1, and +3 would be good choices. So let's see what happens. Now notice here in our first derivative that the bottom is always squared. So the bottom is always going to be positive. So we really just want to worry about the sign of the top. So always positive. So if the numerator is positive, then the whole derivative will be positive. When we plug in -3, we're going to get -60 in the top. So we already know that it's negative. When we plug in -1, it's also negative. And when we plug in +1 and 3, we get +20 and +60 respectively. So our whole thing's going to be positive. So like I've said before, sometimes you don't actually have to plug in the numbers and get a numeric answer because you can just look at what the denominator and numerator are doing independently and see what the sign pattern is going to be. So from this, we can figure out if we have any relative extrema, which it looks like we have one sign change going here from the negative to the left of 0 to the positive on the right. And we know by the first derivative test that if we're going from a negative derivative to a positive derivative, that we have a relative minimum. So we have a relative minimum at 0. And we already found the y-coordinate there to be 9/2 because it's also our y-intercept. And then we can also read off where we're increasing and decreasing here. So let's do our increasing intervals first. So it looks like we're increasing between 0 and 2. And then again, from 2 to positive infinity, just reading off where those plus signs are. And then we're decreasing to the left of 0, so we're doing that from negative infinity to -2, union -2 to 0. And we can't just say from negative infinity to 0 because it stops at negative 2 and there is no derivative there, so it's not decreasing. And it's because there's a vertical asymptote there, so the graph can't be increasing or decreasing because the graph doesn't exist at negative 2. Okay, so we have all of this information now. So now let's find our second derivative and find out about the concavity and see if we have any inflection points. So again, we're going to use our quotient rule and we're going to take the derivative of the first derivative. So derivative of the top is going to be 20 times x squared minus 4 squared minus 20x, so the top, times the derivative of the bottom, which we're going to have to use our chain rule here. So we're going to get 2 times x squared minus 4 times 2x all over the bottom squared, so that's going to come out to be x squared minus 4 all to the fourth power. So now let's just simplify. So if you notice, both my terms in the numerator have an x squared minus 4, and there's 4 of them down there in the bottom, so I can actually cancel some of these out. So I can take the square power and make it a 1, and completely cross out this one over here. And when I do that, I just make my exponent in the bottom a 3, and then I'm just going to simplify with my coefficients. So I'm going to distribute my 20 into the first x squared minus 4, so we're going to get 20x squared minus 80. And then here, I'm going to just have to multiply my negative 20x2 and 2x. So I'm going to get minus 80x squared, it looks like. And then all over that x squared minus 4 quantity cubed, which means that my final second derivative looks like it's going to be negative 60x squared minus 80 all over x squared minus 4 cubed. So again, now we want to look where our critical values are. So this is going to be undefined when x equals plus and minus 2 again, because of that x squared minus 4 in the bottom. And so now we want to set it equal to 0. So when we set it equal to 0, we're really looking at where the numerator of the function is equal to 0. So we move that 80 over, we get 80 is equal to negative 60x squared. Okay, so when we divide by negative 60, we're going to get negative 80 over 60 equals x squared. Which actually we don't even have to keep going from here because now we have that x squared equals a negative number, which can never happen because a number squared always has to be positive, so we actually have no solutions here. Okay, so it means that for our sign chart for our second derivative, we just need to look at where those critical values were where it was undefined. So we just need to look at these two, the negative 2 and positive 2. So we're going to pick 3 test values. So why don't we do negative 3, 0, and positive 3. So let's see. Oh, sorry. So here's our finalized second derivative, just so it's easy to find. So when we plug in, let's do the 0 first. We're going to get negative 80 over negative 4 cubed. So we're going to have a negative over a negative, which is going to become a positive. So put a positive in there. And then it's going to take a little bit more work to do the 3's. So if we plug in negative 3 into the second derivative, negative 3 squared is positive 9. Positive 9 times negative 60 is going to be negative 540 minus 80. So the numerator is definitely negative, so let's just see what's going on in our denominator. In the denominator, we're going to get 9 minus 4 cubed, so we're going to get 5 cubed, which is 125. And so this is a negative over a positive, so overall we're going to have a negative second derivative there. Let's see what happens at positive 3. So at positive 3, we're actually going to get all of the same numbers because positive 3 and negative 3 squared are the same thing. So again, we're going to get negative 540 minus 80 over positive 125. So again, we're going to have a negative over a positive. So we'll have a negative second derivative. So even though we have sign changes going on for our second derivative, like we go from a negative here to a positive and then back to a negative, we actually don't have any inflection points because they're happening over those vertical asymptotes, not at a point that's defined on the function. So we can write no inflection points, and then we can write our concavity intervals. So we're going to be concave up between -2 and +2, and then we're going to be concave down on those outside intervals. So from -infinity to -2, union 2 to +infinity. Okay, so now let's go back up to our graph. We're going to put all of this information on it. So let's split this down into intervals first. So let's look at this interval down here in the corner first. We know that in this interval, so to the left of -2, we found that we were, let's see, let's scroll down to our increasing and decreasing. We found out that we were decreasing from -infinity to -2. We were also concave down. So that means we need to draw a curve in here that is going to approach that horizontal asymptote and approach the vertical asymptote that meets the decreasing and concave down. So we know that concave down is like an upside down bowl, and we know that decreasing means that our y values are getting smaller as we move to the right. So our curve is probably going to look something like this. Okay, so now let's move into the next interval where we have that, whoops, I keep hitting that button, where we hit that y-intercept, so right here in the middle. We knew in that interval that we were, oops, that we're decreasing from -2 to 0 and then increasing from 0 to 2, and we're also concave up. So in this interval from -2 to 0, I'm decreasing and concave up. So I'm probably going to draw something that looks like the first half of a parabola. And then at 0, I switch to increasing, but I stay concave up. So we're going to get something like this. And now all we have to do is this last interval over here, from +2 to +infinity, which we found out that we were, again, decreasing and concave down, I believe. Yep, it looks like we were decreasing from, we're increasing from 2 to +infinity, but we are concave down. This needs to go away. Okay, so if we're increasing, it means as we move to the right, our y values are getting larger, and we're concave down still. So our curve is going to look something like this. So there you go. That's your picture for 2 times x squared minus 9 over x squared minus 4. And if you check it on your graphing calculator, you'll see something very similar. So a thing that's really important for curve sketching is knowing how to combine those increasing, decreasing with concave up and concave down. So we have 4 different types of curves that we could see. So if we're increasing and concave up, we're going to look something like this. And if we're increasing and concave down, we're going to look something like this. So you just want to basically flip the curve around. And the other two deal with when you're decreasing. So when we're decreasing and concave up, we're going to look a little bit like that. And then when we're decreasing and concave down, we're going to look just like we were in that first interval that we did on the graph. We're going to look something like this. So sometimes when I'm doing a curve sketching problem, I like to draw these 4 pictures somewhere on my paper because that way it makes it a little easier to see what sort of curve I should be drawing and what interval on the graph when I'm trying to put all that information together, because it is a lot of information to squish onto one picture. Okay, so thank you so much for watching. Have a great rest of your day.